Welcome everyone to arguably the most important tutorial of the Stacking Sats challenge. In this video, we'll go over a example strategy that will serve as a template for developing your own strategies. In this video, I'll be using the virtual environment that we set up in the previous tutorial. So go ahead and watch that if you haven't already. But jumping right into it, we have a sort of backup plan or a sort of an option of last resort if you haven't set up a virtual environment or for some reason don't want to set up a virtual environment. You could go ahead and turn this markdown cell into code, and there will be some helpers that help you get the required packages and the appropriate versions that this challenge requires. This is what our evaluation engine will be using. I strongly recommend to use the virtual environment, but that's just there in case you need it. Let's go ahead and run all the cells so I don't have to do that line by line. We start off with some global variables that we will be using. The backtest windows defined here along with the cycle and the min weight. So if these global variables are not familiar, go ahead and watch the intro or the challenge overview videos that describe what the challenge is. I'm assuming that everyone here is familiar with all that. So here we just have some general boilerplate code. We're going to be calling the Coinmetrics API to get our historical Bitcoin price data. Then we're going to save that as a CSV and reread it as reread that CSV just to mimic what will happen when we run your model's code on our end after you submitted it. Here we have some more helpers that will help us evaluate your strategy, your model, and additionally some helpers that will plot it and allow you to see what your model is outputting. But other than the boilerplate that is above this cell and the boilerplate that is below this cell, the only code that you will be modifying is in this cell here. So you'll see that there is a helper called construct features and a helper or a function called compute weights. And it has its own signature that you should respect that takes in a data frame and outputs a series, which are going to be the weights, of course. So we're going to dive into our example and use this as a template so you can get inspo for defining your own models. We start off with a helper that defines our features, and one important point is that we shift our price series by one day when we define our features so that we avoid any sort of forward-looking bias. And the best way to explain that is if we're interested in the 200-day moving average in this case, on any given day, we don't know the closing price of Bitcoin. We know the closing price of Bitcoin on the day prior and any day that came before that. So to take this into account, you should shift your data before defining your features just to avoid any forward-looking biases, which will be checked for when we evaluate your model. In this case, we're simply going to use the 200-day moving average as our core feature. The standard deviation is going to be used as somewhat of a supplementary feature. I'll go over that in more detail later on. Now, I've commented out this address here and this decorator that registers our strategy. This is specific to submitting the code, submitting your model for the challenge. So I'll talk about that in the next tutorial. For now, you can just leave that there and ignore it as commented out code. This function here is the core logic for your model. it tells us a deterministic model, a deterministic rule for defining how you're going to accumulate Bitcoin based on whatever feature that you have derived from the price series. In our case, we have two parameters in this model. We have a rebalance window and an alpha parameter. We'll dive into those when they come up. We go ahead and make a copy of the data frame that's being passed in and define the data frame that we're working with that also includes the feature columns. So we call our helper here. Now, we also do some more setup. We restrict our data to the backtest window, and we initialize the weights series. Now, going down here, the problem is based on cycles. So there's 3 4-year cycles in the backtest window, and what we're doing here is we're grouping that data from the backtest start to the backtest end into those 3 separate groups. And we initialize our weights for each of those cycles as uniform weights. And in the quantitative strategy overview, we went over we dive deeper into the reason as to why we do this, and ultimately it's to ensure that we can define weights in an iterative manner, in a non-forward-looking manner, while still ensuring that we satisfy the property that per cycle we use up exactly our entire budget. So without initializing your weights as the uniform weights, it starts to become very tricky to not peek into the future while still ensuring that you spend exactly your entire budget. So we strongly recommend initializing the weights as uniform weights and then creating informed decisions that deviate away from the uniform weights. Now, once we have each cycle, within that cycle, we can start iterating over the end days. And we have this Boolean that checks whether the strategy is active, and that's set to true to begin with. And now we can observe our data. We can observe our shifted price, namely the closing price of the day before. And we can observe our features that we've defined through our helper construct features. So in this case, we have the 200-day moving average and the 200-day standard deviation. Now, making sure that the data is there and it's not null or anything, we have our rule, our deterministic rule for defining how much to purchase based on our feature. And the general high-level idea is that if the price is below the 200-day moving average, namely if today's price is below the 200-day moving average, then this is a time where we can get more bang for our buck and we would want to purchase more. But rather than turning this into a binary outcome of when we do observe this signal, we buy a certain amount, but when we don't, we buy some other amount, we turn it into a continuous outcome by defining a z-score. So by doing that, we take into account the actual distance between the price and the 200-day moving average. Namely, the further the price is, or the higher the discount, the more we are willing to purchase on that day. It indicates some sort of continuous desirability for that day. So that's where that what I call supplementary feature comes in. The standard deviation allows us to define that z-score. And this is also where our first hyperparameter comes in, our parameter comes in, alpha. we simply boost that day's purchase amount, that day's weight, using the z-score and alpha. So now that we've done that and increased the spending on that particular day where the signal is present, we do have to track the excess budget that we're introducing. So we introduced a baseline weight of 1 over n for each day, but now on this particular day we spend more than 1 over n. We've boosted that amount. So now we have to redistribute and rebalance. And that's where the second parameter comes in. And it's a subjective choice. Technically, on day I, if you boost because you observe a particular signal, you could rebalance the excess on all days I plus 1 all the way to day n, which is the end of the Fourier cycle. In our case, we redistribute only in the last rebalance window days of the cycle. So in this case, rebalance window is 2 years. So that means the only time that we're going to start discounting and removing some of the excess budget is in the last 2 years. One way to think about why we went with this decision is it simply creates this bias of purchasing more in the first 2 years and purchasing less in the next 2 years. Typically, with Bitcoin, if you've purchased earlier, you were better off. But that's a very simple way of going about it. I'm sure that there are more nuanced and sophisticated ways of rebalancing. Now that we've talked about the rebalance, there is this aspect that if we purchase or if the signal is popping up way too often and we're boosting a lot of our purchases in the first n, we already used the parameter n, so I'm not going to use that anymore. In the first k days, there is this concern that we might run out of days in the rebalance window to redistribute because there is a minimum weight that you need to purchase every day. So that's essentially where this Boolean comes in, the strategy active Boolean, that if we find that we don't have any more days to redistribute from, then we will switch this Boolean to false and say, well, we've already observed all the signals that we possibly could, and we've boosted on those days. Now, if we continue to boost, we don't have enough days remaining to redistribute that excess amount to ensure that we meet the budget of 1. So the strategy basically stops at that point in time. That's ultimately the main logic of this simple 200-day moving average model. And the reason as to why we provide it as a baseline model is, one, it's a feasible solution. It satisfies all the criteria that this challenge expects, and it's quite simple. It's very easy to explain, and it covers all the key points that we care about, which is respecting the balance and redistributing and starting off and initializing with uniform weights and deviating away from that when necessary. Once you have your compute weights function that essentially defines your model, you can now see what the remaining boilerplate code produces for you. So those plotting helpers will show you your price, and they will also show you your feature. And in this case, it will show you, it will label the purchases, the historic purchases over the backtest window, whether you purchased uniform amounts or if the signal was apparent and you've purchased dynamically, namely you've boosted in some sort of way. You can also explore what those weights look like over each 4-year cycle. And we can see that the dashed line here is the uniform weight. So if we were just doing a uniform strategy, we would just see a uniform line across all 3 of these cycles. However, of course, we have some dynamic aspect to our strategies. And we could also see here that in the later 2 years, in the rebalance windows, where we make up for the excess amounts that we've purchased in the first 2 years. This is specific to the way that we've defined our model. Here it's very important we see that the budget each cycle is exactly 1. The weights sum up to 1. And we have some statistics regarding our model's results. The key point is that we have this check. So the helpers that test out your strategy did not see any forward-looking biases, and apparently believes your model is ready for submission. There's one more thing to check in the next tutorial, which is your model's logic might be appropriate. However, there might be some flaws in the environment. So rather than running the code locally, we use a library that will run your code, and that will make sure that not only your model is appropriately defined, but also you're using the right packages and package versions, and that will mitigate any possible case scenario where the code runs on your machine but it does not run on our end after you've submitted it. And in the very first tutorial, we saw that this black box model, which we've just covered, outperformed the uniform dollar cost averaging approach, namely the regular dollar cost averaging approach. So we see that here. In the next video, it will be very quick. It will just go over a rundown of doing one last check. But for now, this template should motivate you to think about all the possible ways that you could compute your weights that differ from this baseline. And the hope is that you can improve on this baseline, and by doing so, you'll also be improving on the standard dollar cost averaging approach. See you in the next video.